Did you know that you could weld without heat? Brace yourselves for a peek into the mysterious art of seamlessly fusing metals together using cold welding, defying conventional notions of heat and flame. Prepare to be amazed as we uncover the secrets behind this fascinating process and delve into its profound significance in various fields. Cold welding, often referred to as solid-state welding, is a mesmerizing technique that brings together metal surfaces without the aid of heat or melting. Yes, you heard that right. Unlike traditional welding methods that employ intense heat to liquefy metals, cold welding relies on the sheer power of molecular attraction to create an unbreakable bond. It's like witnessing a magical handshake between atoms, leading to an extraordinary joining of metal parts. But how does this enchanting phenomenon occur, you may wonder? At its core, cold welding is a result of a phenomenon called contact welding. When two meticulously cleaned metal surfaces come into intimate contact, the atoms at the interface form strong atomic bonds, resulting in a unified structure. The process is propelled by a combination of mechanical pressure and interatomic forces, which work in harmony to forge a bond of unparalleled strength. Now, let's take a moment to appreciate the profound importance and relevance of cold welding. This innovative technique opens up a world of possibilities in industries ranging from aerospace and automotive engineering to electronics and even space exploration. By eliminating the need for heat, cold welding not only simplifies and expedites the assembly process, but also minimizes the risk of thermal distortion or damage to delicate components. Moreover, its ability to join dissimilar metals adds an extra dimension to design flexibility, enabling the creation of hybrid structures with exceptional performance characteristics. The implications of cold welding are awe-inspiring. Imagine a spacecraft hurling through the vastness of space, constructed with an impenetrable bond that withstands extreme temperatures and gravitational forces. Picture intricate electronic devices, expertly assembled with precision and durability, thanks to the invisible embrace of cold welding. The possibilities are limited by only our imagination, as this remarkable technique continues to shape the forefront of technological innovation. Now that we have set foot in the mesmerizing world of cold welding, let us delve deeper into the captivating process itself. Prepare to witness the intricate choreography of atoms and the role that cleanliness, pressure, and metallic bonding play in this remarkable phenomenon. At the heart of cold welding lies a simple yet profound principle. Clean surfaces are essential for a successful union. When two metal surfaces come into contact, any contaminants, such as oxides, oils, or other impurities, act as barriers, preventing a strong bond from forming. Therefore, meticulous cleaning of the mating surfaces is paramount, often achieved through various methods like solvent cleaning, ultrasonic cleaning, or even etching. This ensures a pristine environment for atoms to engage their captivating dance of solidarity. Once the surfaces are impeccably cleaned, the stage is set for the main act, the application of mechanical pressure. This force acts as the catalyst, driving the metal atoms closer to each other. As the surfaces make intimate contact, the real magic begins. The atoms at the interface respond to pressure by engaging in a profound embrace, creating a bond that is both intimate and unyielding. Now let's shine a spotlight on the factors that influence the cold welding process. First and foremost, as previously mentioned, cleanliness is of utmost importance. Even the tiniest impurity can hinder the formation of strong metallic bonds, compromising the integrity of the joint. Therefore, rigorous surface preparation and cleaning procedures are meticulously carried out to eliminate any potential roadblocks. Next, we have the role of pressure. The magnitude of the applied force determines the effectiveness and strength of the resulting bond. Higher pressure allows for a greater degree of atomic intimacy, facilitating the intermingling of atoms across the interface. However, it's important to strike a balance. Excessive pressure may cause deformation or damage to the metal surfaces, compromising the overall structural integrity. Now let's cover metallic bonding. In cold welding, when the metal surfaces make contact, the atoms arrange themselves in a manner that maximizes the attractive forces between them. This atomic bonding occurs through a process called diffusion, where atoms migrate across the interface and intermix with their counterparts from the other surface. As a result, a solid-state bond is forged, characterized by the sharing of electrons and the establishment of interatomic forces, ultimately creating a strong and inseparable connection. The power of metallic bonding is nothing short of mesmerizing. It enables the creation of joints that possess remarkable strength, often surpassing the strength of the parent materials themselves. The intimate interlocking of atoms ensures a seamless transition across the interface, allowing for the transmission of mechanical forces and electrical currents without hindrance. Cold welding, with its captivating ability to unite metals without the need for heat, has garnered significant attention and found a multitude of applications across various industries. Today, we will focus on two fascinating realms where cold welding shines brightly: micro-electromechanical systems and space applications. Prepare to be enthralled by the incredible possibilities that unfold within these domains. In the realm of MEMS, Where miniaturization and precision are paramount, cold welding emerges as a game changer. MEMS devices consisting of intricate components at a microscopic scale require meticulous assembly techniques that preserve the integrity of delicate structures. Cold welding provides the perfect solution, allowing for the bonding of miniature parts without subjecting them to the potential thermal damage caused by traditional welding methods. MEMS devices span a wide range of applications, including sensors, actuators, microvalves, and accelerometers. By employing cold welding, these devices achieve enhanced performance, reliability, and durability. The seamless joining of components through atomic-level bonding ensures precise functionality, improved signal transmission, and resistance to harsh environmental conditions. From medical devices to consumer electronics and beyond, the impact of cold welding on the MEMS field is profound and far-reaching. In the vast expanse of space exploration, where extreme conditions prevail, cold welding proves to be an invaluable ally. Traditional welding techniques relying on heat are challenging to implement in the vacuum and extreme temperature variations of outer space. Cold welding, with its ability to bond metals at ambient temperatures, offers an ideal solution for constructing spacecraft, satellites, and instruments that withstand the rigors of space. The implications are immense. Imagine spacecraft constructed with intricate metal joints that exhibit unparalleled strength and resilience, ensuring the safety of astronauts and the success of interplanetary missions. The absence of heat-induced distortions and weak points enhances the structural integrity of space-bound vehicles, enabling them to endure the forces of launch, extreme temperatures, and the harsh environment of outer space itself. Moreover, cold welding facilitates the repair and maintenance of spacecraft during long-duration missions. By carrying along spare parts made of compatible metals, astronauts can utilize cold welding to seamlessly replace or repair damaged components. This capability reduces the reliance on Earth-based support and paves the way for self-sustaining space exploration. Beyond MEMS and space applications, cold welding continues to find relevance in fields such as automotive manufacturing, electronics, jewelry making, and more. Its versatility and reliability have positioned it as a transformative process, revolutionizing the way we join and assemble metals across a diverse range of industries. When it comes to joining metals, two distinct techniques vie for supremacy: cold welding and traditional welding. Each method brings its own set of advantages, limitations, and areas of application. Let's compare the differences between these two processes. The most apparent disparity between cold welding and traditional welding lies in the application of heat. Traditional welding relies on intense heat to melt and fuse the metal surfaces, creating a molten pool that solidifies to form a bond upon cooling. In contrast, cold welding accomplishes the joining of metals at or near ambient temperatures without the need for heat. The process relies on molecular attraction and mechanical pressure to forge a bond. Traditional welding often requires specialized equipment such as welding machines, power sources, filler materials, and shielding gases. The process involves precise control of heat, welding parameters, and often complex techniques to achieve the desired weld quality. Cold welding, on the other hand, typically involves simpler equipment such as mechanical presses or specialized tools for applying pressure. The absence of heat-related complexity makes cold welding comparatively simpler in terms of equipment requirements. While traditional welding can join a wide range of metals, cold welding is more effective when working with similar or compatible metals. Cold welding success depends on the ability of atoms to intermingle and form strong atomic bonds across the interface. Metals with similar crystal structures and lattice parameters are more likely to achieve successful bonding through cold welding. Traditional welding, with its ability to melt and fuse dissimilar metals, offers greater flexibility in joining different types of metals. Traditional welding methods often subject the welded components to significant heat, resulting in thermal distortion and the generation of residual stresses. These effects can lead to warping, bending, or changing in the overall shape of the welded structure. Cold welding, being a solid-state process, minimizes the risk of such distortions, contributing to the preservation of the original form and dimensional accuracy of the joined parts. Both cold welding and traditional welding can create strong, durable joints. However, the joint strength achieved through cold welding is often comparable or superior to the strength of the parent materials themselves. The atomic level bonding achieved in cold welding ensures an intimate interlocking of metal atoms, resulting in joints with exceptional integrity and mechanical properties. In summary, cold welding and traditional welding represent two distinct approaches to joining metals. Traditional welding relies on heat and melting, offering versatility and the ability to join dissimilar metals. Cold welding, with its solid-state bonding at ambient temperatures, excels in precision applications, microassembly, and environments where heat-induced distortions or thermal damage are concerns. Both techniques have their unique strengths and limitations, catering to different requirements across various industries. Through the power of molecular attraction and mechanical pressure, it forges unbreakable bonds without the need for heat. The process of cold welding begins with meticulous surface preparation, ensuring pristine cleanliness free from impurities. With intimately contacting metal surfaces, atoms engage in an enchanting dance, forming atomic bonds that are both intimate and inseparable. Through diffusion, metals intermingle, creating a unified structure that boasts exceptional strength and durability. In the world of metal joining, cold welding stands as a testament to innovation and adaptability. It defies boundaries, unites metals with a touch of magic, and unlocks new possibilities in fields ranging from microscale technologies to space exploration. By embracing the art of cold welding, we unlock a world of extraordinary bonds where science and imagination collide. As always, thank you for taking the time to learn with me. If I missed anything or got anything wrong, please let me know, as I would love to learn more. If you liked what you heard, please consider subscribing. If you did not like what you heard, thank you for sticking with me this far. I appreciate the time you've taken watching this video. No matter who you are, you only get 24 hours in a day. Thank you for spending a portion of that with me. See you next time.